The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're talking about what happens when antibiotics and chicken collide. We'll speak with Maryn McKenna about her new book, Big Chicken, and with Tara Smith about life on the front lines studying antibiotic resistance. Welcome to Science for the People. I'm Bethany Brookshire, a writer with Science News and Society for Science and the Public. Chicken. Maybe you think it's finger-licking good, or the healthy option that sits next to the vegetables in your low-carb diet. Or maybe you don't eat it at all. But on average, people in North America eat a lot of chicken. But they didn't used to. Maryn McKenna is an award-winning journalist and author of the book Superbug and Beating Back the Devil. She's written for Wired, National Geographic, Scientific American, New York Times Magazine, Nature, and more, and is a senior fellow at the Schuster Institute for Investigative Journalism at Brandeis University. I like to call her the scary disease lady because when there's a new antibiotic-resistant bug, I can trust Maryn to tell me just how scared I should be. In her new book, Big Chicken, The Incredible Story of How Antibiotics Created Modern Agriculture and Changed the Way the World Eats, coming out September 12th, Maryn talks about the rise of the modern chicken dinner and what it means for the health of us and our feathered friends. Maryn, thank you so much for joining us.
Thank you for having me.
Now, this book is partially about chicken and partially about antibiotics. Why did you end up choosing chicken as your model for antibiotic use in livestock? Why not cows or pigs or lamb?
So it turns out that chicken actually plays a central role in this larger story of how we came to give antibiotics to almost every meat animal on the planet and how we discovered that was a terrible idea. And the role the chicken plays is that chickens were the first animals to get experimentally what came to be called growth promoter antibiotics. And in the United States, at least, it looks like poultry will be the first, let's say, sector of the protein economy that's going to exit routine antibiotic use. So chicken, in addition to being the meat that we eat more than any other in the United States and the meat that's growing fastest in around the globe, it turns out to have this arc that embraces the entire story of using antibiotics routinely in agriculture that isn't really matched by any of the other animals that we eat.
And I think most people know that antibiotics are used in agriculture, but most people also think of antibiotics as something that you just take when you're sick. And please note to the audience, only take antibiotics for bacterial infections and not for viruses. Thank you. Now,
So what you just expressed is really what got me into this story 4 years ago now, maybe a little bit more than that. Because as somebody who writes about science and medicine and had spent most of my career sort of pursuing epidemics and disasters, I had a very settled sense that what we do with antibiotics in human medicine is that we give them to people who are sick. Now, as you just said, we try to give them only to people who are sick with bacterial infections, right? We try not to give them to people with viral infections, and we try to discourage people from misusing antibiotics. But all across medicine, there's this sense that antibiotics are a thing that we use for one goal, and that is curing infections. So then I stumbled across the story of how we use antibiotics in agriculture, and it just fundamentally made no sense to me because most of the antibiotics used in agriculture, better than 90%, do not go to animals that are sick. They go to animals that are well for reasons other than curing infections. They go in this manner that I just mentioned that's called growth promotion to make animals fatter, essentially, to make them deposit muscle tissue more rapidly. And they go to animals in a preventive sense to keep them from catching diseases in the concentrated conditions that most meat animals are raised in. But they don't actually go to sick animals. And it was that disjunction between this is what we do in humans and this is what we do in animals and it's different that made me want to dive into this story.
Yeah, and I found it was very interesting how this whole story kind of got started. So I was wondering if you could tell me a little bit about the man Thomas Jukes.
So Thomas Jukes is a Brit who's living in America. He's a chemist, essentially. He's an expert in the biological needs of chickens. Like, what do they need in their diets? And to understand why that's important, I have to set the scene a little. So if you went back to the turn of the last century, to the like 1910, 1920, there were chickens around. There were plenty of chickens, but they were all essentially backyard chickens. There was no industrial poultry production as we know it today. People had chickens largely to produce eggs. They didn't grow chickens only for meat. And at a certain point, after the hens had laid a certain number of eggs, usually when they were about 2 years old, people killed them and they ate them. Or if the eggs hatched out to male chickens, into baby roosters, they usually killed them pretty young and ate them. And those were actually tender and tasty. They're what's come down to us now as spring chickens. But there was no keeping chickens all year round. And the reason for that was that no one had figured out how to keep chickens' diets consistent. And then in the 20s and 30s, people figured out how to synthesize vitamins. And this is a thing that Jukes was involved in. And so suddenly there was a diet that you could construct artificially and give to animals all year round. And you wouldn't have to worry about them running out of insects that they'd been pecking in the barnyard because it was winter and the insects were no longer present. So suddenly it's possible to keep chickens year-round. Jukes is part of this. He's a rising star in sort of agricultural nutrition. And at the same time, after he's been doing that for a while, several other things are happening. The first is the start of the antibiotic era. So I think everybody at some point hears the story of Alexander Fleming with his dishes of bacteria. Something blows in the window, mold grows on his dishes, and he realizes that what is excreted by the mold is killing the bacteria in his petri dishes. And from that, we get the first antibiotic, penicillin, which is a compound produced by the mold. What I think most people don't know is that Fleming does that in 1928, but we don't actually get penicillin as a drug until the early 1940s. There's a long gap in which Fleming doesn't really know what to do with this compound he's discovered. And then he gets some collaborators who figure it out. And the advent of World War II makes it urgent to have something to cure people, especially soldiers on the battlefield. So penicillin in the early 1940s suddenly changes the world. And at the same time, the war ramps up enormously the need for protein. So there's huge new infrastructure built in cattle, in pigs, and in poultry production to feed the troops that are deploying millions of troops all around the world. And then the war ends. That infrastructure isn't needed anymore. There's a crash in the protein markets so that they need to reduce their costs. It's the beginning of the era of the wonder drugs. Other manufacturers are following Fleming by discovering streptomycin and tetracycline and chloramphenicol, and they want to find markets for them. Now, you would think that curing infections would be a good enough market, but Jukes happens to work for one of the manufacturers of one of the first antibiotics, Lederle Laboratories, part of American Cyanamid. They make chlorotetracycline, the first of the tetracycline class. And Jukes gets the idea through some ideas that have been sort of percolating through what I guess we can call the beginnings of pharmaceutical chemistry, to try to feed chickens, his specialty, with the leftovers from tetracycline manufacturing. And he does that at the end of 1948. And the chickens to which he feeds the waste products from tetracycline manufacturing grow so much bigger in the same amount of time as a control batch of chicks and as bunches of other batches of chicks that have gotten different supplements. And suddenly an industry is born.
And you do say so much bigger. How big are we talking here? I mean, I think a lot of people who live in North America today, to me, a chicken breast is big. It's bigger than my hand.
Right, exactly.
It didn't used to be that way. How big were these chickens in comparison to the old style chicken?
So I have to sort of voice a caveat before I say these numbers, because the chickens that we have today are not only the result of antibiotics and routine antibiotic use over decades. There's also been intensive crossbreeding, and there's also precision nutrition that didn't exist at the beginning of the 20th century. But allowing for all those things that together, those three strands of nutrition, genetics, and antibiotics that make up the modern chicken, There's a university that keeps the genetic strains of chickens from various years through the 20th century. Some of their scholars wrote a paper a few years ago, and their 1957 strain chicken at the age of 56 days, which is a bit longer than most chickens in America. We mostly slaughter them between the ages of 38 and 50 days. At 56 days, a 1957 chicken weighed 905 grams. So that's a little less than 2 pounds. A modern chicken, the genetic strain that would match what genetics companies were selling in 2005, at 56 days, weighed 4,202 grams. That's more than 9 pounds.
That is just a mind-boggling number.
But what you expressed about chicken breast, that's sort of the real world example of what's happened. That one half of a chicken breast, the half on one side of the keel bone, is bigger and thicker than your hand. And there's actually a problem in the restaurant industry now in that chicken wings, which are everybody's favorite snack and thing to eat in the bar, chicken wings are getting too big, so that in weight, a serving of chicken wings might only be 5, at most 6 pieces of wing, drumettes or flats. And for most customers, visually it's not enough, even though individually it might be a fair amount of ounces of chicken. To look at a dish and only see 6 pieces of chicken, people feel kind of cheated by it. So there's a really intense discussion right now between essentially food production and food service, trying to figure out if chickens are too big, not because they're concerned about antibiotic use, but because they are not matching customer expectations. When you have a chicken breast that's bigger than what you're going to put the breast in for a sandwich, then you have a problem and you need to dial that back.
That is, I don't even know what to say to that. But antibiotics were wonder drugs. They were wonder drugs for humans, and now they're wonder drugs for chickens. And farmers, of course, really wanted in on this. I was really struck by this part of your book because people already did know that antibiotic resistance could happen. You mentioned Alexander Fleming, the discoverer of penicillin. He actually warned about it when he received the Nobel Prize, and people had already seen resistance to antibiotic drugs by the mid-1940s. But when people discovered these growth promotion effects, nobody even paused. No one said, oh, hey, why did they just go in on this? Why didn't anybody stop and say, hey, maybe resistance?
So in order to report this book, I read a lot of old journal articles, old pieces of research, many of them not digitized. I spent a very significant amount of money buying old bound volumes of conference proceedings that had never been digitized, so I could kind of track what scientists were saying to each other back in the 40s and 50s. And it is correct that right from the start, people were worried about antibiotic resistance as a result of antibiotic use in medicine. And that makes sense, right? Because what antibiotics are at their base is they are our version of the compounds that bacteria level against each other to compete for living space, for sources of nutrition, for space for their descendants. They're essentially bacteria's chemical weapons. So we took those compounds into the lab and we refined and standardized them. And since bacteria had been resisting each other's attack for millennia before we ever came along, it would have been naive of us not to think that process would continue. And so the first resistance against penicillin, which is most people consider it the first antibiotic. Sulfa drugs come before it. They're an antimicrobial, but penicillin is made by an organism. And so most people consider it the first antibiotic. Penicillin's first human test is in 1941. It gets rolled out on the battlefield in 1943. It becomes public in 1944, but the first penicillin resistance is reported in 1940. Before any of that happens in the lab. And the first real world resistance really starts moving across the globe in the early 1950s. So people were aware that if you use an antibiotic, you risk resistance, that the prescription of an antibiotic is always a balancing act between the risk of provoking resistance and the benefit of achieving a cure. So why did they not think about this when they were using antibiotics in animals? One reason probably is that most of the doses that we're talking about which you can call subtherapeutic doses because they are not actually enough to kill an organism, were really, really small. The first dosage for growth promoters was 10 grams of active antibiotic per ton of poultry feed. Vanishingly small. It's amazing that it even created an effect, and yet it did. But some of the early investigators did actually attempt to interrogate this. And what they looked at with the kind of crude molecular tools they would have had in the 1950s was the question of whether bacteria in the animal's guts, because these antibiotics are being given in feed and water, would they become resistant? And what they concluded, falsely as it turned out, was that resistance would probably happen. But if it rose to a certain point, say a certain percentage of bacteria in the gut, they thought the antibiotic effect would just stop working, that the growth promoters would no longer promote growth, and that would be a signal that the process was no longer working. But they kept on thinking of that as something confined to the animal. The problem that they didn't anticipate, and the reason why it's necessary to talk about antibiotics in agriculture, is that they never considered what would happen if those resistant bacteria migrated away from the animal into the wider world. And that's the real reason why antibiotic use in agriculture is such a problem. It's not just that we're giving antibiotics in a way that isn't really necessary or that betrays antibiotics' highest purpose. It's because it creates resistant bacteria that depart from the animals, move away from farm properties, get into the environment, into air, into dust, into ground and surface water, cross to humans through all those pathways, and also through the meat that the animals become, and cause drug-resistant infections in people that can be very serious. That's really the concern that underlies all of this.
And one of the things that antibiotics also allowed, in addition to the growth promotion and, of course, eventually the development of antibiotic-resistant bacteria, is they actually kind of allowed chicken farming to just become very, very different. And I was particularly struck by the fact that before the advent of antibiotics in agriculture, people didn't really eat a lot of chicken. I was kind of wondering if you could talk a bit about Jessie Jewell and chicken raising and how chicken became I'll just have the chicken that it is today.
So the reason why I love this story of chicken and antibiotics and wanted to spend 4 years of my life on it is that there are so many different strands that braid together to make this history. And one of them is that several people, but really this amazing guy, Jesse Dixon Jewell, who was from a very poor family up in the poor hills of northeast Georgia, saw an opportunity in all the things that were starting to happen in poultry production to create a new kind of business. So as I said a little while ago, if you go back more than 100 years, chickens were just the thing that everybody had out their back door. And they were there mostly to produce eggs, and then they got killed when their egg laying years were done. Or if they were baby male chickens, they got killed fairly fast because they were young and tender and they were kind of pointless in the barnyard. So that was, everybody had some chickens, but nobody had poultry production. And then the innovation starts to happen. And, there are the diets, the jukes improved. There's the electrical incubator, which allows for artificial incubation of eggs. So you no longer have to lose a certain number of months of your hen's life sitting on her own eggs. But behind all of this, there was always just a chicken. And a chicken, it's kind of hard for us to think our way through this, given that we live surrounded by chicken nuggets and, chicken cold cuts and chicken hot dogs and chicken sausage. But chicken used to be kind of hard to eat because it is a bird that has a lot of bones in it. It's not like a cow, which is a big, unwieldy thing, but when you cut it up, has large swaths of muscle that are not necessarily interrupted by bone. And the same for pigs. There's rather more meat per bone on a pig than there is in a chicken. Chickens are full of bone. And so they were kind of hard to eat and kind of hard to cook. And so there was only like a chicken that you could buy in a store, which meant you had to roast it or maybe cut it up and fry it. Everything you did with a chicken was kind of messy and time consuming. And so chicken had a sort of demand problem. And even as the supply of chicken after World War II and through the 1950s got better and better and better, people didn't really want to eat that much chicken because it was a pain in the neck to deal with. And eventually innovation comes along in the person of a Cornell professor named Robert Baker. And he is charged by his department, the Department of Poultry Science at Cornell, with finding other things to do with chicken. And he comes up with almost all the things we can think of today that are the other ways that we eat chicken. But the reason why he should probably have a monument to him is he is the father of the chicken nugget, developed not by McDonald's in 1980, but by Robert Baker in the basement of a Cornell laboratory in 1963.
I love this, and I just adore the idea that he's basically the original Chick-fil-A cow, like eat more chicken.
He is. There were, it's amazing. You know, I live in Atlanta. I live less than an hour's drive from where Jesse Jewell got modern chicken production going by essentially recreating sharecropping in chicken instead of in row crops. We think of the Southeast as the center of chicken production. And before the Southeast, probably the Delmarva Peninsula, because that's the first place where a woman, actually, Mrs. Cecile Steele, the wife of a Coast Guard officer, thought to raise chickens not just for her own use, but to sell to restaurants and hotels. But it turns out that way up there in the Northeast in Cornell actually is an important point in the story of chicken. That's a spot that nobody really thinks of when they think of like, why did chicken grow in America? Upstate New York is not a place that would come to mind.
One of the things the antibiotic use in chicken led to was the wonderfully futuristic contest to create the chicken of tomorrow. Can I get an echo on that? Chicken of tomorrow. Maryn, can you talk about this contest? Because it's wonderful.
I know, isn't it amazing? The first time I tripped across I couldn't believe that this actually existed. But it did exist. It existed back in the late 1940s. So again, to remember, weirdly in chicken, lots of things are happening at the same time. So diets are improving and electric incubators are invented and antibiotics come into the picture and modern poultry production starts. But chickens are still fundamentally genetically the things that were running around in people's barnyards, which are chickens that are adapted to scratching around in the dirt and eating bugs and living a long time. And those were primarily, again, those were egg-laying chickens that secondarily ended up as meat. No one really had bred a pure meat chicken to that point. And people started to think about this, that maybe they could solve the problem of people not wanting to eat enough chicken by changing the chicken, not just changing the way that we present the chicken on the plate, which was what Robert Baker does and comes in the 1960s. But before Robert Baker, there is the Chicken of Tomorrow contest, which is sponsored by, thought up by, the chain that we now call A&P supermarkets. They decided they wanted to stimulate innovation in the space of chicken. And with the help of the USDA, what they do is they declare a nationwide contest to make a better chicken just by breeding, right? We are not in the realm of transgenic chicken at this point. So they say there's going to be this massive national contest. People are invited to breed chickens that they want. This is what one of the leaders of the contest said in 1947 in the Saturday Evening Post. He envisioned a chicken chunky enough for the whole family. A chicken with breast meat so thick you can carve it into steaks, with drumsticks that contain a minimum of bone, all costing less instead of more. And there just wasn't that much meat on a chicken relative to the other things that chickens did at that point. So they declare this contest. Thousands of people enter. And finally, in 1948, it comes down to just a handful of contestants who have perfected a breed of chicken essentially in their backyards, breeding out of sort of the standard heritage lines of chicken. And they have sustained their personal breeds long enough so that it's stable over several years so they can bring them to the contest. And they bring eggs that have all been timed to hatch at the same time to an agricultural station at the University of Delaware. And they're all put in pens. And they put the white chickens next to the dark chickens so that if a chick accidentally tumbles over the edge of the pen, they'll know they'll be able to fish them out and put them back where they belong. And they grow them up. And they slaughter them all, and they pluck them and clean them and do all the things you do when a chicken is dead, and then they present them to the judges. And in the end, someone wins the chicken of tomorrow. And then there's a runner-up who wins like the second best chicken of tomorrow. And then a couple of years later, they do it again. And the person who wins the first chicken of tomorrow contest also wins the second chicken of tomorrow contest. And from those chickens, we get almost all the lines of what come to be called broiler chickens that we eat today. All of the people who won or placed in the chicken of tomorrow contest in 1948 and 1951 are turned into the companies that dominate the industry today.
That's way more successful than like any Project Runway contestant ever.
It's amazing.
In particular, in your book, you talk about the work of Stuart Levy in looking at this transition from, not farm to table really, but farm to human in terms of antibiotic resistance and in terms of bacteria. Can you talk about that particular experiment? It was very clever.
So Stuart Levy is he's still alive. He's still on the faculty at Tufts University outside Boston. And he's an extremely clever researcher. And how he ends up testing the impact of antibiotic use in chickens is really a very interesting story. So you have to step back a couple of years. The first big outbreaks of antibiotic-resistant foodborne illness occur in England, or at least they're noticed in England. And I actually grew up in England, and my best sort of guess for why this happened is that in England, being a fairly small place, agriculture and urban life are much more interpenetrated than they are here in the United States. So I remember, that the town that my family lived in when I was a kid, you didn't go very far outside that town before you saw fields of sheep and cows. Whereas here in the United States, we have put most of our agricultural production, including protein production, way away from most of the population centers. So agriculture for us is kind of out of sight, out of mind, and not something that we can see and make an intellectual connection to. So in England, they get to be concerned enough in the late 1960s about antibiotic resistance traveling to people by means of food that they declare a government commission that studies the problem for 2 years and ends up recommending that England be the first government on the planet to ban the routine use of antibiotics in agriculture. This comes out of a commission that is called the Swan Commission for the person who heads it, Michael Swan, who was the Chancellor of Edinburgh University and went on to become chairman of the BBC. And because England does this, it's proposed in 1969, it becomes law, it's passed by Parliament in 1971. There's suddenly a lot of pressure in the United States to see whether we shouldn't be doing this too. And so our FDA starts studying whether antibiotic use in animals should be curbed in some manner. And this has grown enormously. I mean, within 5 years of Jukes' first experiment, there were 500,000 pounds of antibiotics were being used in American farm animals. And that was still in the 1950s. So by the time you get to the 1970s, there's already vast quantities of antibiotics being used. So the FDA starts to say to the manufacturers who hold the licenses for antibiotics to be used in this manner that they are beginning to be concerned. And they would like these manufacturers to start researching whether there's been an unintended consequence of the deployment of their drugs in this manner. And so one of the big, essentially, lobbying groups, the groups that, take care of the political interests of agriculture and veterinary pharma, goes looking for researchers to do experiments for them that will prove that the connection does not exist, that there is no connection between antibiotic use on the farm and antibiotic-resistant illness in humans. And they pick this rather young, not very well-known researcher, Stuart Levy, who is working in Boston, and they say they will fund this experiment for him. Will he please try to figure this out? And he says, yes, he will. So he decides that what he needs is he needs something like a farm that isn't a farm. And he goes looking on the outskirts of Boston for a property that can be made to act like a small farm, a model farm, but on which animals have not been raised recently, so that there won't be any confounding influences, no prior antibiotic use, no prior bacteria lurking around. And through just a sort of a chain of network of people who know each other between Boston and the suburbs, he happens across a family who have a big old property that long ago had been an egg sorting and packaging firm. So it's got barns and it's got space for animals and it's got lots of kids, because the couple who own this property have decided to take in lots of foster kids from the town and give them a home and raise them. And so Stuart Levy gets introduced to them and he goes out to meet them. And the father of the family actually grew up on an agricultural property in South Massachusetts, and he laughs at this professor from the city and says, "You have no idea what you're proposing." And the professor, to give him credit, says, "Yes, you're right. I don't, and I need you to help me. Will you help?" And so they do. And what they do is they subdivide the family's biggest barn into pens. And then they go and they buy chicks. And they also go and they buy just standard commercial feed for the chicks that you can buy in any feed store. They buy feed that doesn't have antibiotics and feed that does. And then they give the feed to the chicks, sequestering the chicks that are getting the antibiotic-laced feed in such a way that they can't get anywhere near the chicks getting the antibiotic-free feed. And then they wait to see what happens. And they sample the feces of the chickens and the feces of the humans, of the family, the parents and the kids. And it becomes very clear, very rapidly, antibiotic-resistant bacteria arise in the guts and are expressed in the manure of the chickens that are getting the feed laced with antibiotics. But then the chicks that are getting the antibiotic-free feed also start expressing bacteria that are resistant to the antibiotics that the other chickens were getting. And then the same bacteria start to show up in the guts and in the poop of the people who are taking care of the chickens. And that, for the first time in a prospective manner, proves that antibiotic-resistant bacteria arise in animals as a result of their being fed antibiotics and cross to other animals on a farm and also cross to the humans taking care of them. And it's so dramatic a finding that it actually leads to action in Congress to try to change antibiotic use in agriculture in the United States, which unfortunately turns out to be unsuccessful.
Yeah, a lot of this evidence kind of mounted and mounted, and every single time the government would just say, "Oh, it's not good enough, we need another study." But it kind of feels like the history of antibiotic use in livestock has hit something of an inflection point with the resistance to a drug called colistin. Can you talk about colistin resistance?
Sure. So this is kind of the nightmare bug. So when we talk about antibiotic resistance, I think people get that antibiotic resistance arises when we use antibiotics, and what happens then is that if an antibiotic-resistant organism doesn't respond to an antibiotic, we need a different antibiotic. And so the emergence of antibiotic resistance becomes this sort of game of leapfrog between bugs and drugs that starts in the 1940s and keeps going. You can rely on that game of leapfrog saving you so long as there is always another drug. But what's happening as a backdrop to all of this is that we are running out of drugs. Because resistance emerges so predictably and so rapidly that round about the year 2000, the pharma companies decided that they didn't really want to make antibiotics anymore. I mean, when you look at the new drug approvals at the FDA, it gets to about the year 2000 and it just falls off a cliff. And from a pharma company's point of view, this makes perfect sense, because if you're going to spend a decade and $1 billion to make a new drug, and you put your new drug out into the world, and in 5 years, 20% of the cases in which you use your drug are not cured, you are probably not going to make back your R&D investment. And if your drug is so amazing that medicine says, "That is such a fantastic drug, we are going to keep it on the shelf until we really need it," you definitely won't make back your R&D. So therefore, we've been running out of antibiotics as resistance has been proceeding. And there are only a few drugs left, really what people call last resort, last ditch antibiotics for the very worst infections. And colistin is one of them. In fact, there are people who consider it the last antibiotic. Now, colistin is a drug that dates back to the beginning of the antibiotic era. And it has lasted this long because it was kind of a crude drug and it had a lot of side effects and people really didn't want to use it. So it sort of lurked at the back of the shelf. But while medicine didn't want it, agriculture adopted it. Not so much in the United States. We don't use colistin in agriculture in the United States, but in Europe and in Asia, colistin was adopted through the 1950s up to the present day and used by the literal ton, not as a growth promoter, but as a preventive drug to protect animals of various species from the infections that they might catch in intensive agriculture. So this didn't really matter because colistin wasn't important. Nobody was going to use it. But as we ran out of other drugs and as bacteria became more and more resistant, people started to look at colistin again as a treatment. And then in 2015, a set of scientists working in China with some collaborators in England announced that they had found resistance to colistin. And they had found it at the same time in pigs, in pork, and in hospital patients. It was conferred by a gene that they came to call MCR, which stands for mobile colistin resistance. And the reason why that's so important is that the quality of this resistance factor was that it was contained on a plasmid, a free loop of DNA that can move easily between bacteria. It isn't only passed down through inheritance to daughter cells, but it can move within the same, widely through the environment, through generations, horizontally through generations of bacteria. So at the point at which they found this resistance, we were already behind the curve. It was announced in November 2015 that MCR existed. And by the middle of last year, MCR had already been found in 34 countries, causing infections in humans, including here in the United States. So that's the rapid movement of resistance to the very last antibiotic that we have as a result of using it freely in agriculture, because it seemed like a drug that medicine had disdained and would never want back.
And now it seems, I think partially because of this and because of, for example, the rise of antibiotic-resistant foodborne illness in the United States and elsewhere, it seems that people are kind of getting, for lack of a better phrase, scared straight. What are people doing differently? The chicken companies are kind of changing things up now, right?
So one of the reasons that I wanted to tell this story, after a career of, oh God, we're all going to die, is that unlike most of the outbreaks that I write about, this story actually has some good news at the end. There are some solutions. There's a solutions piece. And that is that just in the past couple of years, there's been both political action and also, much more importantly, social action, consumer pressure applied to the use of antibiotics in agriculture round about, let's say around 2012, 2013, 14, a coalition sort of self-assembles. It starts, I think, with healthcare institutions who have patients that they feed and don't want to risk that their patients are going to acquire antibiotic-resistant bacteria as a result of what the hospital was feeding them. So hospitals, very large hospital systems and university medical centers say no to meat raised with the routine use of antibiotics. They're joined by very large school systems, like the Chicago schools, for instance. Then kind of like, food movement leaders, chefs especially, start to get into the action. And there's a very significant movement, again, sort of self-assembling, of just everyday parents putting pressure on food production and food service companies to say, we're voting with our dollars. We don't want to do this anymore. And the interesting thing is that, so as I said, way back in the 1960s, England was the first government, the first nation to act against agricultural antibiotic use. And what they did was partial. No one has ever enacted a complete ban. But they were followed by the Scandinavian countries in the 1980s, and then the entire European Union in 99, and then with a more complete version of the EU ban in 2006. The United States had never done anything. We tried back in 1977. There was this pushback from Congress, and so we never did anything. And then the Obama administration comes in 2009, and weirdly, I don't think most people think of this as a legacy of the Obama administration, but in fact, the Obama administration takes antibiotic resistance really seriously and writes an executive order, creates a national strategy, impanels a president's commission, holds a summit at the White House to look at antibiotic resistance. And one of the things that's wrapped up in that is that the FDA finally decides, after more than 30 years of stalemate, that it's going to act on agricultural antibiotic use. And it creates not a ban, as was tried in the 1970s, not a legal regulation, but what they consider a non-binding guidance that nevertheless the agricultural industry gets behind. And it would be my contention that the reason that so much changes, that the industry decides to get behind the FDA's quasi-voluntary recommendation, is because there's so much pressure from consumers, which is much more explicit in the United States than it ever was in Europe. So as a result, we have, Purdue Farms, the fourth largest chicken company in the United States, declaring in 2014 that they are going to go entirely antibiotic free, and Chick-fil-A and Subway and Taco Bell and Tyson and Costco and Walmart, and one after another. It's now more than, I think, 40 or close to 40 companies of various types, both food production and food service, that have declared that they are going to take antibiotic use out of their chicken, at least. Pigs and cows are going to be harder. But chicken is really kind of leading the way. And it's all happened in a really short space of time.
And is that enough? We already have these antibiotic-resistant infections. We have MCR1 on a plasmid. Is that enough? Is getting rid of antibiotics in agriculture going to save us?
So antibiotic resistance is always a both-and problem. If we took all antibiotics out of agriculture and we misuse them in medicine, resistance would still be a problem. And to some degree, resistance will always be a problem because resistance is an inevitable biological process. But the things that we do make it much worse. So there's plenty of antibiotic misuse and overuse in medicine as well. The count is believed to be something like at least 1 in 3 outpatient prescriptions is inappropriate, either because it's not for a bacterial infection or it's a bacterial infection, but it's the wrong drug for that particular bacterium. There's up to 40% misprescription considered to be an inpatient. And that's just in the industrialized West. There's vast antibiotic misuse in agriculture, but also in medicine, including open over-the-counter sales in the global South. So even if we get all of the antibiotics out of agriculture, which we have not done at this point, resistance as a problem is not going to go away. But because it's such an overwhelming problem, any small action, it's like we understand that climate change is an overwhelming problem, but we still do our best to buy better light bulbs. Because every small thing that we do may contribute to ameliorating the problem in some small manner.
And I would like to say that the end of your book is actually surprisingly hopeful, coming from the scary disease lady. Maryn, thank you so much for joining us.
Oh, thank you for having me.
Big Chicken, the incredible story of how antibiotics created modern agriculture and changed the way the world eats, will be out on September 12th. We've linked more information about Maryn and her book at scienceforthepeople.ca. Next, we'll be talking to one of the scientists who studies antibiotic resistance to find out what life is like in not the trenches, but the farms.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skepchick Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back. We've heard from Maryn McKenna about how science helped the rise and now the slow descent of antibiotics in agriculture. But what is it like to be on the front lines of the research? To find out, I'm here with Tara Smith, who studies zoonotic diseases at Kent State University in Ohio. Tara, thank you so much for being here.
Absolutely. Thank you for having me on.
Now, you specifically study zoonotic diseases which spread from animals to people. How do you get into studying stuff like that?
Kind of by accident. My PhD was in very basic science research looking at group A strep that causes strep throat. I moved into my postdoc to do infectious disease epidemiology and worked with a different type of strep. And then when I moved to Iowa for my professorship, I ended up studying Staph aureus, which is kind of a related gram-positive bacterium. And I was in Iowa, which is the #1 pig-producing state. And one of my master's in public health students happened to be a swine veterinarian. He'd worked in the field for about 30 years. And this was when papers were coming out of Europe that looked at swine MRSA. So methicillin-resistant Staph aureus, kind of one of these superbugs that was apparently originating in pigs and spreading into people in the Netherlands and in France. So being that we were in Iowa and he had swine connections, we decided to look at it there. And it's kind of snowballed for about the last 12 years.
I have to say that the phrase swine connections sounds like the memoir of a postmodern comedian of some kind.
It could be. It could be.
Now, you do a lot of work on farms with swine, with other species. What is involved specifically in studying bacteria in livestock? What kind of challenges do you face?
Yeah, I mean, the biggest one is getting on the farm in the first place, and it's only gotten more difficult over the years. When we started this, I was completely unknown. We had a little bit of funding actually from the National Pork Board, who promotes, eating pork and pig health and other types of things. So they funded us for our initial small study. And with the help of our veterinarian, Mike Maley, we were able to get on these farms and catch some pigs and take some nasal samples from the pigs and from the people working with them. But over the years, it's gotten a lot more strict. There are actually some laws now in various states that can eliminate people from being on these farms, that make it illegal in some cases for activists to, take pictures of animals or people on the farms. And so there's just been this big crackdown on really getting onto these farms. And people are understandably a little bit mistrustful. So really getting access is the big problem. Once we have that, it's fairly easy to get in there and, grab some pigs and swab their noses and things like that. That's the easy part, but it's really building the relationships and getting onto the farms that are tough.
And of course, you need to be on those farms because food companies might say that, and have said that there are few proven links between antibiotic use in livestock and antibiotic-resistant infections. Is that true? How do you prove a link like that?
Right. It's really tough because obviously if you don't have the samples from the animals themselves, you can't prove what is coming from which different farms. So we've done some things to, try to get around some of that. We've done a lot of meat sampling. So we can say that at least in, samples of raw pork products or raw chicken or raw turkey that are bought at the supermarket, you can find these types of bacteria. And then we can match those up with people that are carrying, similar types of the staph in our case. But then to prove that, okay, those bacteria came from the farms instead of, somewhere else during processing is very difficult if you can't get on the farms to sample them in the first place. So that's kind of a broken or, missing link sometimes there.
So you buy a lot of this meat from, say, grocery stores. Has it impacted what meat you eat and how you consume your pork products?
It has. I do try to eat meat that is organic or sourced from individuals that I know, like farmers markets that are in the area, from farmers that I can talk to and ask about their antibiotic use. There's a lot of controversy about, organic farming and whether it's better, whether it's not. But at least I think for livestock, in organic practices, you can't use antibiotics at all. So even if an animal needs to be treated for a disease, they will treat it still, but they have to sell it as, not an organic product. So it does cut down on antibiotic use on the farm. You can't use it for growth promotion. You can't use it for disease prevention, which is another big place that antibiotics are used on the farm. So I do think that's important, and I do try to buy organic.
And you were the first person to recognize MRSA, and we've talked a little bit about methicillin-resistant Staph aureus, in livestock in the United States. And now most people know about MRSA. They know people who've had run-ins with MRSA. But there's also a new resistance to the antibiotic colistin. And we've heard a little bit about this from Maryn, but can you tell us how MCR1 is similar to or different from the MRSA that people are familiar with?
Right. So MRSA is in kind of a different class of bacteria. So microbiologists divide bacteria into gram-positives and gram-negatives, and I won't go into all the differences for those, but gram-positives are your Staph aureus, your group A strep that causes strep throat, strep pneumo, which can cause pneumonia and ear infections. So MCR1 doesn't bother those. You use different drugs to treat those. So MCR1 are in gram-negatives, which are a real problem because as we're running out of antibiotics for all bacteria, gram-negatives are really where we're kind of almost at the point of no return, where we have very little to treat them. So colistin resistance, the MCR1 and also MCR2 genes, can be found in gram-negatives like E. coli, like Klebsiella, like Salmonella. A lot of the gram-negatives that cause things like food poisoning, but it can also cause blood poisoning and other things. So they're different in that way, but they're similar in that they both carry genes that can be transferred among lots of different bacteria. So the gene that causes methicillin resistance is called MEK-A, or there's another one called MEK-C, and that gene can be swapped among bacteria. So it's not just, like human genetics where you have this, vertical transmission of genes from mother and father to baby. In bacteria, you can have what's called a horizontal transmission. So it'd be like, me getting a gene for brown hair from you or something like that. So you can get it among kind of adults of the species. So MEK-A for methicillin resistance and MCR1 for colistin resistance can be swapped among these bacteria. So it can spread very quickly. And that's the problem in these populations, is that when you're using antibiotics, you select for those resistance genes because it's very beneficial to be carrying them.
I think of it as like the positive kind of STD. In bacteria, it's really good to be a slutty bacteria because you get all these genes that help you survive the antibiotics.
Exactly.
And the problem with this is that colistin is an antibiotic of last resort in people, but it's used not in North America for livestock, but it's certainly used in Europe and in China. What can we do to make sure that we can still use colistin in people? Is it too late?
Well, we hope not. They are cracking down now on use of colistin in agriculture, in theory, at least as far as some of the policies that are being introduced to try to restrict that. So they're trying to reduce what's out there, to limit some of these selection pressures, to keep these MCR resistance genes from spreading. And again, in the United States, we don't use it in agriculture, and it's still not a very common drug in human use because it does have a lot of, potential toxic side effects, and it's not something you want to give as a first choice. So hopefully with, surveillance, looking for this, knowing where it is, and very close use on colistin use, very close tracking of colistin use in hospitals, we can keep this at a low level as it is right now. But you just never know. Bacteria are ancient. They're smarter than us in many ways, and they've outsmarted us at every step.
And you study this stuff. You've seen that the FDA now has voluntary measures in the United States asking farmers not to use antibiotics as growth promoters specifically. What does that mean? Is there still opportunity to use antibiotics on the farm?
Right. So there still are. So growth promotion use is using these at these low doses to make animals grow faster, to get them to market sooner. So this has been concerning for many years, as Maryn discusses in her book. And we've been trying to get policies introduced to try to regulate these and try to eliminate them, as many other countries have long before us. So finally, producers and pharmaceutical companies decided voluntarily to eliminate the use of growth promotion antibiotics and to necessitate prescriptions for some other type of antibiotic use on the farm. So farmers will still be able to use antibiotics for disease prevention or prophylaxis purposes. So, at certain times during an animal's life cycle, like, for example, when pigs may be moved from a nursery where they, were born and raised for a few weeks to a growing barn where they may, be the rest of their life, that stresses the pigs and it can cause disease to break out. So farmers at some points will give antibiotics prophylactically to prevent these disease outbreaks in the herd. So those will still be able to be used. You can definitely still use antibiotics for treatment. Treatment is something that no one really argues with. If animals are sick, they need to be treated. But what we're concerned about is that this will be, instead of really a real elimination of growth promotion antibiotics, it will kind of be a relabeling so that there may be more prophylactic use, even if growth promotion antibiotics technically aren't allowed. So we're not sure yet, and we won't have the numbers for quite a while, to know if these restrictions will actually lead to a reduction in the overall use of antibiotics on farms or not. We're a little skeptical at this point, but we'll see.
What do you think is the eventual future for antibiotics in livestock?
I think they have to be phased out, even more than they're doing now. Many people have suggested that, these livestock antibiotics really aren't that profitable anymore. They're not giving the profit margins that justify their use. Obviously there are still controversial areas about the effect that they have on human health and disease, even though those of us in public health would say that's been pretty well proven. There are still, holdouts in industry and agriculture that suggest they don't. But I think consumers really are the ones that are driving the bus anymore, that they don't want to consume animals, to purchase animals that have been raised with these types of antibiotic use. So as you see more companies moving towards animals that have been raised without antibiotics, I think that's really going to, and we're already seeing this shift the market, especially in chicken, as Maryn discusses. So hopefully that will move it also in larger animals like pigs and cattle. And we'll really see this market push to animals that are raised without antibiotics.
And I talked a little bit about this with Maryn, but one of the issues with that is, a lot of people may say, well, you help fight this with your dollars. You can say, okay, I am going to purchase only antibiotic-free meat. I'm going to buy my chicken from Whole Foods, or I'm going to buy it organic. I'm going to buy my pork organic. But a lot of that meat is more expensive. And what do you think is going to be the result of that? How do we make sure that people can buy, make those kind of choices regardless of how much money they have to spend?
Right. And it's definitely not a panacea. And there are those of us, who can't afford this right now. And certainly that's not everyone. But I think as more producers start to move toward that type of agriculture, that will bring down the costs eventually. That there are a lot of upfront costs as far as changing husbandry practices, and in some cases maybe enlarging farms or enlarging pens for the animals, that will be built into the price of, your pork chop or your steak or your chicken breast right now. But as that becomes the norm, that hopefully will fall out a little bit over time. And, they may see gains in other places that animals just don't need these antibiotics anymore because they have more room or things like that. And so they'll have some cost savings on that end. So I'm not an economist. I'm hoping that some of that will level out eventually. And in the meantime, those of us who can, afford to buy these types of products and who can afford to kind of push that forward can do so.
Well, Tara, thank you so much for being on the show.
Thank you for having me.
We've linked Tara's blog and more information about antibiotics in livestock at scienceforthepeople.ca. There you'll also find links to Twitter, Facebook, and Apple Podcasts, where you can make like an antibiotic-resistant bug and spread the word about our show in a good way. You'll also find our Patreon page where you can help us out and kick us a few bucks per month to help us spread the scientific word. Thanks for listening, and we'll see you next week on Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.